what should be the discriminant? What do you think? Try to think about this. See, delta was difference of roots squared. How would you try to define the discriminant in terms of the roots? So the roots of this equation are, let's suppose R1, R2, R3. What will be your definition of the discriminant? Let's take another hint from this. What happens if I interchange the roles of alpha and beta? I get beta minus alpha squared. It's the same thing as alpha minus beta. So the discriminant is symmetric as a function of alpha and beta. Because I really don't know which one is alpha, which one is beta. Alpha and beta are simply names, these are symbols. So the discriminant doesn't depend on the labeling of the roots. Anyone can be alpha, anyone can be beta. So this gives us another hint. Your discriminant should be a symmetric function of these three roots. Symmetric function. Which means if I do a permutation of R1, R2, R3, relabel them in a different way, I should still get back the same answer. Okay? So it turns out that here is the right definition. R1 minus R2 squared, R2 minus R3 squared, R3 minus R1 squared. This is my definition. Alright? Now what I will do is, I will try to write this in terms of the roots that I know. Please note the roots are Z1 plus Z2. R2 is Z1 omega plus Z2 omega squared. R3 is Z1 omega squared plus Z2 omega. Right?
How do we get the discriminant?
How do we get it? Okay. See again, all the clues are contained in the quadratic case. You have studied that the discriminant tells you exactly the nature of the root. And if you express in terms of the roots, it's exactly alpha minus beta squared. So this encodes the information, nature of the roots. When are they complex conjugates? When are they real and distinct? And when are they equal? So I want a similar analysis for a cubic case. The roots are R1, R2, R3. I want to be able to say when are the roots real. I want to be able to say when are there complex conjugates, and so on and so forth. So, I mean, your question is very well founded. At this moment, I can only give you this as an answer. Right? Right. So, so if you plug all these things in and simplify, delta turns out to be a very, very interesting number, very interesting expression rather. It turns out to be minus 108 times it is not a typical calculation. Maybe in the evening today some of you should try. Just plug these values in and use the fact that they are roots of this equation. So, the nice thing is, please note, there is no Z1, there is no Z2 here. There is no omega. Everything is expressible in terms of these coefficients. Because this is a given data. If I give you a reduced cubic, you know what P and Q are. You can write down this. right? And do you recognize this? Q squared by 4 plus T2 by 27. This was exactly the expression under the square root sign when we were finding Z1 and Z2. Remember that? So, the conclusion, so here is a statement that one can prove. So, can prove, number one, that if, so, delta is equal to 0 exactly when the reduced cubic, which I will call as star, has 3 real roots. Sorry, this is false. This is a precise statement. Delta equals 0 exactly when star has, delta will be 0. When will this be 0? When at least one factor is 0. So you have a repeated root. Right? Exactly when star has repeated roots, and hence this is something you can prove. All roots are real. Delta less than 0 exactly when there is one real root and 2 complex conjugates. So this is the analog of what you have studied for the quadratic case. Write down the discriminant, look at the sign of the discriminant, and that should tell you the nature of it. So in this case, delta is positive exactly when you have 3 real roots, delta is 0 exactly when you have repeated roots, and all the roots are real. Okay? And finally, delta is less than 0 exactly when there is one real root and complex. And this also answers part of our confusion. I will remind what that was. Please remember this expression for z cube or z1 cube, doesn't matter. You have the same expression here in delta. Yeah? What happens when delta is positive? How can delta be positive? You already have a minus 108 here. So this expression has to be negative. Yeah? Which means that when you find the square root, you actually get a complex number. And you are getting the cube root of a complex number. And please think about this. The theorem says that when delta is positive, that means this term is negative, you actually get real roots. This is exactly the situation which you encountered. Remember our example? Y cube minus 7 pi plus 6 equal to 0. Your expressions were very complicated. You had 10I divided by 3 root 3. This theorem says that in this case, you can find the square root cube roots. And when you add up the cube roots correctly, you in fact get real roots. So it's funny, it sort of works, in a different way. How can delta be negative? So you want this to be positive. If this is positive, this is great. It's just a real number. But then the theorem says that you actually get 2 complex conjugates. Because you are taking the cube root. And there are 2 possibilities which I am not writing down. Z1 omega plus Z2 omega squared and so on. Alright. So this completes the discussion for the cubic case. Are there any questions or comments? Has everybody understood this algorithm? Okay. So so what happens for degree 4 polynomial? So I will not describe this in detail except that I will make just 2 comments. Let's start with a okay. I can make the first change of variable x equal to y minus a by 4 now, and this will remove the cubic term. You can remove it. You will get something like this: x to the 4 plus px squared qx plus r equal to 0. Okay? This can always be done. And now there exists an algorithm to find the roots of this. But if you follow that algorithm, if you study it carefully, you will end up with a cubic in another parameter. You have to first solve that cubic, and then you will get all the roots of this degree 4 polynomial. So it's very interesting that way. Please look at the hierarchy of these algorithms. Quadratic, only one idea was needed: complete squares. For cubic, you needed to first reduce it, and then you actually get a quadratic in z cube. Remember that? Yeah. So the degree 3 algorithm depends on the quadratic case. Or degree 4, I am saying, is it depends on the cubic. So by induction, degree 5 should depend on degree 4, etc., etc. Right? So there exists a formula for the root. Alright? So please remember the dates. Whatever we discussed goes back to the 1550s. The quadratic case was known 2000 years ago, so there was a jump of 1500 years before you could actually handle degree 3. The degree 4 case was solved pretty soon after this. But then people struggled a lot to answer the same question for degree 5 and higher. Given a quintic, a degree 5 polynomial, is there a formula in terms of the coefficient? The people struggled a lot, and nobody succeeded. And then there was a very, very beautiful theorem due to Abel and French mathematician Galois. This was in 1820s. They proved that there is no such formula to solve for the roots of a polynomial of degree greater than or equal to 5. You cannot have an algorithm in terms of the coefficients of the given polynomial. Please make sure you understand this properly. I am not saying that It's not possible to solve a degree 5 polynomial. It's very much possible. To take x to the 5 equals 1. I will tell you 1 is a root. And if 1 is a root, by long division you have a quotient of degree 4. And I can tell you what the roots of degree 4 polynomial. No, that's not what I mean. I mean that there is no formula involving the coefficients of the given polynomial. One would imagine that I take the fifth root of some complicated quantity, the fourth root of something complicated, cube root of something. No. There is no such formula in terms of the coefficients. So we have to rely on the hit and trial method. But that doesn't work, unfortunately. So solving equations is a fundamental problem in mathematics. What we have discussed are very, very beautiful arguments, algorithms. And here is a very, very remarkable case. Says that you cannot hope to do this to degree 5 and higher. So one has to rely on numerical methods, and there are lots and lots of schemes, but that's a different story. So I think I want to stop here. I'll be very happy to answer questions. We can have a discussion if you like. Let me stop here. Yes.
Can you ask any other questions?
Oh, sure. Feel free. Yes.
There is a question.
Trigonometry. Well, maybe we can do that later. I thought you had something about this.
Every time you have to make the coefficient of x cube starting at 1 and starting of the.
Yeah, you can always divide out by that coefficient, right?
How do you do that?
No, if you can like, put ax cube, no problem. But then your formulas will become more complicated. That's all. Yes.
Both sides divided by
Yes.
both those sides.
Can you say that again? If I take the cubic, then?
Then divides by both sides.
Yeah. So you're asking about why do we take the deduction?
Sir, question is y cube plus 4y plus 7 equal to 0.
Y cube plus 4y plus 7 equal to 0. Yes.
Then y cube plus 4y plus 7y equal to 0y.
Yes.
The second equation is y square plus 8 plus 4 plus 7y equal to 0.
Yeah. But then you have 7 by y, huh? So it's not a degree, it's not a quadratic, it's actually a cubic. Because it's 7 by y, it becomes a rational function. Okay, so you have to do this. Yeah. Okay. So the question is about this three possibilities. So I wrote down the discriminant as minus 108 q squared by 4 plus p cubed by 27. I was only trying to tell you to compare it with the formula for the root. Alright. So the point I was trying to make is, when is delta positive? Delta is positive provided this term is negative. Isn't it? Q squared by 4 plus p cubed by 27 is less than 0. This implies this. Right? And if this is negative, watch what happens here. So, you are taking the square root of a negative number. So you already have a complex number here. And I am taking the cube root of that. And that's going to be another complex number. And the theorem says that if delta is positive, you actually have three real cubes. So this is not a contradiction. simply means that once you find out the cube roots, they always exist, and you simplify it out, everything will cancel, leaving only the real. And that's what happened in the example. Y cubed minus 7y plus 6. The roots are 1, 2 and minus 3. But look at the calculations that you did. You had 10i and so on and so forth. So you have to take the cube root of that and simplify. To simplify, so this is not really a contradiction. So any other questions or comments? Yeah. Yes. It's too big. Yeah, you have to solve a cubic first. You have to solve a cubic. I can explain it, but okay. So I'm just trying to emphasize this point. The degree, solving degree 4 means you need to be able to solve a cubic, which I have told you. That's good enough, I think, for the time. But you should know that there is a form where the algorithm exists. Yeah. Y is equal to, yes, okay. Okay, that's a very nice question. So the question is, why did I take, for the quadratic, why did I make this transformation? Okay. Now can somebody tell me what the graph of a quadratic equation looks like? What are the possibilities? Parabola. The parabola can either point upwards or downwards. It can either intersect the x-axis or not intersect. Isn't it? Okay. Suppose it intersects. These are the roots that I am trying to find. Alpha beta. What happens when you make this transformation? Y minus a by 2. This is a transformation along the x-axis. X is getting changed to y minus a by 2. And the effect of doing this is the coordinate system shifts so that the parabola becomes symmetric about this line. Yeah? Can you tell me, this is a parabola, everybody said. Yeah? What is the vertex of this parabola? How will you find the minimum or the maximum of this? I give you a function x squared plus ax plus b. Can you tell me the critical points of this function? You studied calculus, right? No, doesn't matter. Anyway, the thing is, this transformation, what it does is, it actually shifts the coordinate system so that your y-axis divides, is exactly, at the midway of alpha and beta. So that the sum of the roots becomes 0. That's exactly what happens. When you simplify this in terms of y, you get y squared plus a constant equal to 0. For this quadratic, the sum of the roots is 0. Yeah? So that is the effect of doing this. And for a cubic, if you write x equals y minus a by 3, it is doing precisely the same thing. The coefficient a is the coefficient of x squared, which is the sum of the roots, r1 plus r2 plus r3. And when I divide by 3, you are actually taking the average of these three roots. So you are shifting your y-axis in such a manner that the average of these three roots is 0. So it's like, moving to the center of mass frame. You might have learned in physics that you can deal with the center of mass frame. Calculations become simpler there. That's exactly what it is. I don't want to disturb the x-axis because if I shift the x-axis down below, then this function has no roots. I'm not interested in this. I want to capture the roots, if any. So the only transformation I'm allowed to make is movement of the y-axis. I can shift left or right, but not up or down. up or down creates or destroys roots. I don't want that. Okay, so this is the geometrical meaning of y minus a by 2. Any other questions or comments? So anyway, this theorem that I wrote down, there is no formula in degree 5 or higher. This theorem marks the beginning of what is now called modern algebra. Modern algebra is no more about calculating very, very big expressions. It's actually understanding symmetries. It's actually understanding the core of why such a formula exists and why it does not exist. Right? So the term modern algebra refers to a very, very different thing altogether than what is taught at the college level. Okay? So it's a very fascinating study of symmetry associated to a given mathematical setup. Yes.
So we know that cube root of 1, there are only one cube root, there is 1. So you told us new cube roots, omega and omega square, what are they?
What are they? Okay. So out of 1 omega and omega squared, only 1 is the real cube root. Omega squared and cube roots are complex. Okay. So cube root of 1 simply means you solve the equation Z2 equals 1. So degree 3 polynomial. And there is a fundamental theorem which says that if you have a polynomial of degree n, then it has exactly n roots in the complex plane. It's a fundamental theorem. So you expect 3 roots. The other 2 are complex. Okay, so I think I'll stop here. So thank you very much.
For your inspiring talk, and I hope you all enjoyed the session. Please give the opportunity to learn from you, sir.
Yes.